On October the 29th, 2025, something extraordinary happened that almost nobody could witness. The interstellar visitor, designated 3I/Atlas, reached perihelion, its closest approach to the Sun, at a distance of 1.36 astronomical units. For context, that places the object roughly 40% farther from our star than Earth orbits, nestled in a region between Earth and Mars, where solar heating reaches intense but not catastrophic levels. Under normal circumstances, astronomers worldwide would train every available telescope on such a visitor during this critical phase. Perihelion represents the moment of maximum solar flux, when surface ices sublimate most vigorously and hidden materials emerge under thermal stress. This is when comets reveal their deepest secrets, when their true composition becomes visible through spectroscopy, when structural weaknesses manifest as fragmentation events. But 3I/Atlas chose the worst possible geometry for human observation. At perihelion, the object positioned itself almost directly behind the Sun as viewed from Earth, disappearing into what astronomers call the solar exclusion zone. This region of sky, extending roughly 30 degrees on either side of our star, becomes effectively invisible to ground-based telescopes. The Sun's overwhelming brightness drowns out even relatively bright objects passing through nearby space. Attempting to observe anything in this zone resembles trying to spot a firefly hovering beside a searchlight beam pointed directly at your face. The photons simply cannot compete. The timing could not have been more frustrating. 3I/Atlas, the third confirmed interstellar object ever detected passing through our solar system, arrived at its moment of peak activity precisely when Earth-based civilization lost all ability to watch. For approximately 6 to 8 weeks surrounding perihelion, the object would remain hidden behind solar glare, its behavior unknown, its evolution unmonitored. Every major observatory on the planet became useless for this target during the most scientifically valuable phase of the entire encounter. This blackout differs fundamentally from clouds blocking a telescope or equipment failure preventing observation. Those obstacles are temporary and localized. The solar exclusion zone represents a geometric inevitability, a blind spot built into our position in space. No amount of technical sophistication or observational skill can overcome the basic physics of line-of-sight obstruction. When an object passes behind the Sun from our perspective, it vanishes as completely as if it ceased to exist. The implications depend entirely on what 3I/Atlas actually is. If astronomers are correct that it represents an exotic but natural comet formed in another stellar system and ejected into interstellar space, then the observational gap, while scientifically frustrating, carries no deeper significance. We miss data. We lose understanding of how the object responds to peak heating, but the universe continues operating according to natural law whether we watch or not. But if 3I/Atlas is something else, something artificial, as Harvard astronomer Avi Loeb has suggested might be possible, then perihelion takes on different meaning entirely. An engineered probe traversing interstellar space would need energy. Solar panels or equivalent technology could harvest power most efficiently at closest approach to a star. Thermal management systems would face maximum stress requiring active cooling or orientation changes. Navigation corrections through outgassing or solar sail effects would achieve greatest efficiency when solar photon flux peaks. Coarse, alterations executed during perihelion could redirect the object toward new targets deeper in the solar system. And all of this would happen while Earth cannot see. The solar exclusion zone does not merely hide 3I/Atlas from view. It creates an information asymmetry, a window of time when the object could theoretically alter its behavior in ways that would remain undetectable until weeks later when it emerges back into observable sky. By then, any changes to trajectory, brightness, or morphology become fait accompli, observable only in their results rather than their execution. The geometry feels almost surgical in its precision. 3I/Atlas approached from interstellar space on a trajectory that threaded encounters with Venus, Earth, Mars, and eventually Jupiter, all while reaching perihelion behind the Sun during the most critical observational window. Natural orbital mechanics can produce such configurations through pure chance, but the convergence of so many low probability elements in a single object strains comfortable explanations. So we wait, blind, while the visitor does whatever it does in the zone of silence. Perihelion is not just another point along an orbit. It represents a moment of transformation when an icy wanderer from the distant reaches of space encounters the full force of stellar radiation. For 3I/Atlas, October the 29th, 2025 marked this critical transition when the object reached 1.36 astronomical units from the Sun and crossed into a thermal regime unlike anything it experienced during millions or billions of years, drifting through the frozen void between stars. The physics are straightforward but profound. Solar heating intensity follows an inverse square law, meaning that as distance from the Sun decreases by half, the energy delivered to each square meter of surface increases by a factor of 4. At its discovery distance of several astronomical units, 3I/Atlas received gentle warming, enough to begin liberating the most volatile ices, like carbon monoxide and carbon dioxide. But at perihelion, solar flux reaches levels that can sublimate deeper reservoirs of frozen material, potentially exposing layers that formed during the object's birth in another stellar system billions of years ago. This is when hidden chemistry reveals itself. Comets behave like archaeological sites, with stratified layers encoding their formation history. Surface materials sublime first as solar heating increases, followed by progressively more refractory compounds requiring higher temperatures to vaporize. Water ice, frozen for eons in interstellar darkness, begins transitioning directly from solid to gas. Carbon dioxide, already detected by the James Webb Space Telescope as the dominant volatile in 3I/Atlas's coma, reaches maximum sublimation rates. More exotic species like ammonia, methane, or complex organic molecules could emerge if they exist within the nuclear ice. The outgassing process is not passive evaporation. As gas escapes from the surface, it carries dust grains embedded in the ice matrix, creating the diffuse coma and tail structures visible from Earth. The rate of mass loss peaks at perihelion, potentially shedding thousands of kilograms per second, depending on the size and composition of the nucleus. This represents the object's most active state, when spectroscopy can detect the widest range of molecular species, and when morphological changes happen most rapidly. Thermal stress also tests structural integrity. If 3I/Atlas consists of loosely aggregated materials held together by ice acting as cement, perihelion heating could weaken those bonds. Historical examples like comet Linear in 2000 demonstrate how thermal stress fractures comet nuclei, sometimes producing spectacular fragmentation events where a single object splits into multiple pieces. The alternative, survival intact through perihelion, indicates either strong internal cohesion or a composition more resistant to thermal degradation than typical dirty snowballs. For an artificial object, if such a thing were passing through our solar system, perihelion offers maximum available solar power. Photovoltaic surfaces would generate peak electrical output. Thermal gradients between illuminated and shadowed regions would reach maximum values, potentially useful for energy harvesting or attitude control. Any systems requiring activation after a long dormant cruise through interstellar space would logically power up when energy availability peaks, and we cannot see any of it happening. The solar exclusion zone exists as a fundamental consequence of physics, not equipment limitations or atmospheric interference. When an object passes behind the Sun from Earth's perspective, it enters a region where observation becomes impossible, regardless of telescope size, detector sensitivity, or image processing sophistication. The Sun emits such overwhelming brightness that attempting to observe nearby objects resembles trying to photograph stars at noon. The scattered light, glare, and sheer photon flux create an impenetrable observational barrier extending roughly 30 degrees on either side of the solar disk. At perihelion on October the 29th, 2025, 3I/Atlas positioned itself at 1.36 astronomical units from the Sun, which translates to approximately 204 million kilometers. From Earth's vantage point, however, distance matters less than angular separation. The object appeared less than 30 degrees from the solar limb as measured across the sky, placing it firmly within the exclusion zone, where ground-based telescopes cannot acquire useful data. This geometric arrangement would persist for 6 to 8 weeks as 3I/Atlas slowly moved along its trajectory, while Earth continued its own orbital motion. The problem extends beyond visible light astronomy. Radio telescopes, which normally operate independently of daylight and can observe through clouds, face their own challenges with solar proximity. The Sun radiates powerfully across the entire electromagnetic spectrum, including radio wavelengths. When a target lies near the Sun in the sky, solar radio emissions create noise that drowns out faint signals from distant objects. The solar corona, an extended atmosphere of superheated plasma surrounding the Sun, generates additional interference through scattering and refraction of radio waves passing through or near this turbulent medium. Space-based observatories in Earth orbit gain no advantage over ground-based facilities for objects in solar conjunction. The Hubble Space Telescope, floating above atmospheric distortion, still cannot point within 50 degrees of the Sun, without risking permanent damage to its sensitive instruments from scattered light entering the optical system. The James Webb Space Telescope maintains even stricter solar avoidance angles, keeping its massive sunshield between the Sun and its cryogenically cooled infrared detectors. These constraints exist by design, protecting expensive instruments from thermal damage and optical contamination. But they create blind spots precisely where 3I/Atlas now travels. The timing of perihelion passage through the exclusion zone was not deliberately chosen by the object itself, at least not in any way that violates physics. Orbital mechanics dictate that any trajectory bringing an interstellar visitor through the inner solar system will eventually carry it near the Sun. The date and geometry result from the object's velocity vector upon entering the planetary region, combined with the Sun's gravitational influence and Earth's position along its own orbit when perihelion occurs. Natural processes produce these configurations routinely, yet the convergence of multiple factors creates an observational gap during the most scientifically critical phase of the encounter. 3. Atlas reaches maximum solar heating, maximum outgassing activity, maximum thermal stress on its structure, and potentially maximum brightness, all while positioned where no Earth-based asset can monitor its behavior. The object entered the zone in late October and will not emerge into observable sky until late November or early December, by which time its perihelion passage will be weeks past, and any transient phenomena will have already concluded. We can calculate what should be happening based on models and physics, but we cannot verify those predictions through direct observation. The geometry has rendered us blind at precisely the moment we most need to see. Before 3I/Atlas disappeared into the solar exclusion zone, there was supposed to be a preview, a close encounter with Mars that would provide crucial baseline data for understanding what the object might do at perihelion. On October 3rd, 2025, the interstellar visitor passed within approximately 29 million kilometers of the red planet, close enough for spacecraft orbiting Mars to observe it from a vantage point far superior to anything Earth-based telescopes could achieve. Multiple space agencies had months to prepare observation campaigns using assets already positioned around Mars. The scientific community anticipated detailed imaging, spectroscopy, and morphological data that would resolve ambiguities left by more distant observations. The European Space Agency operates Mars Express and the ExoMars Trace gas orbiter, both equipped with high-resolution cameras and spectrographic instruments. NASA's Mars Reconnaissance Orbiter carries the HiRISE camera, capable of resolving features as small as 30 centimeters on the Martian surface. When pointed at 3I/Atlas during closest approach, these instruments should have achieved pixel scales of approximately 30 kilometers, enough to distinguish between a compact nucleus and diffuse coma structure. NASA also maintains the MAVEN orbiter and the Perseverance rover on the surface, the latter carrying the Mastcam Z camera system that could potentially capture night sky observations if mission planners allocated time for the attempt. The timing seemed perfect. Mars assets would gather comprehensive data from close range, establishing a detailed observational baseline before the object reached perihelion weeks later. By comparing pre-perihelion Mars observations with post-perihelion Earth observations, after 3I/Atlas emerged from behind the Sun, researchers could quantify exactly how solar heating altered the object's properties. Changes in brightness, spectral signatures, coma morphology, and outgassing rates would all become measurable through this before and after comparison. Then, the United States government shut down. On September 30th, 2025, a funding lapse forced NASA to cease non-essential operations, including most public communications and data releases. The shutdown affected timing rather than capability. Spacecraft continued operating autonomously through pre-programmed sequences, and international partnerships remained intact. But the immediate flow of information to the public slowed to a trickle. Press releases stopped appearing. Image galleries stopped updating. The usual rapid dissemination of exciting findings from active missions gave way to bureaucratic silence. What made the shutdown particularly provocative was not that it prevented observations, but that it coincided almost perfectly with the Mars flyby window. October 1st through 7th represented the prime observation period, and the government funding lapse began just days before. While European spacecraft operated normally and presumably collected their planned data, NASA's assets fell under communications restrictions that delayed or prevented timely public release of whatever they observed. A citizen scientist named Simeon Schmaus posted stacked Mastcam Z-frames on social media, showing a faint blue smudge at the predicted position of 3I/Atlas. Harvard astrophysicist Avi Loeb amplified the image, lending it credibility through institutional association. But NASA never officially confirmed or refuted the detection. No follow-up images appeared. No processed data from HiRISE or other Mars orbiters entered public archives with tags indicating 3I/Atlas observations. The silence persisted even after the shutdown ended, so the scientific community entered the perihelion blackout period without the Mars baseline data that should have informed their understanding. The closest look anyone would get at 3I/Atlas before it disappeared behind the sun remained locked in agency servers, or simply never happened due to observation scheduling conflicts. Either way, we lost the preview that would have told us what to expect when the object emerged from solar conjunction weeks later. The observational blackout during perihelion carries different weight depending on what 3I/Atlas actually is. If mainstream astronomers are correct that the object represents an exotic but fundamentally natural comet, then the gap in our data amounts to scientific frustration rather than existential concern. We lose valuable measurements of how an interstellar visitor responds to peak solar heating. We miss opportunities to refine compositional models and outgassing mechanisms. But the universe continues operating according to natural law, whether human observers watch or not. The physics unfolds predictably, even without telescopes pointed at the action. But the possibility that 3I/Atlas might be something else transforms the blackout from inconvenience into strategic vulnerability. An engineered probe traversing interstellar space would face critical operational requirements at perihelion that align almost too perfectly with the observational gap. Solar power generation peaks when photovoltaic surfaces receive maximum flux, providing energy levels impossible to achieve during the long dormant cruise through the darkness between stars. Any systems requiring activation after millennia of hibernation would logically power up when available energy reaches its maximum. Thermal management becomes equally critical near perihelion. An artificial structure would need to maintain internal temperatures within operational ranges despite external heating that could vaporize conventional materials. Active cooling through directional outgassing, rotating to distribute thermal load across different surfaces, or deploying reflective shields, all require energy and generate observable signatures. But these activities would be most intense precisely when Earth cannot see them happening. Navigation presents perhaps the most significant possibility. Small course corrections executed at perihelion achieve disproportionate effects on final trajectory through the gravitational slingshot effect. A probe could alter its path to target specific destinations deeper in the solar system, adjusting its approach to Jupiter Saturn, or other bodies of interest. The delta V required for meaningful trajectory changes scales inversely with distance from the Sun, meaning that a given amount of thrust produces far greater orbital modifications when applied at closest approach. Outgassing directed in specific directions, solar sail effects from a reflective surface, or even conventional propulsion, if such systems existed, would all be most efficient during the perihelion window. And all of these potential activities would occur behind the Sun, where no Earth-based observer could detect them. By the time 3I/Atlas emerges from solar conjunction in late November or early December, any changes to its trajectory, orientation, or operational state become observable only through their results. We would see the outcome rather than the process, the new orbit rather than the maneuver that created it, the altered brightness rather than the surface reconfiguration that caused the change. The timing creates what intelligence analysts would call an information asymmetry. One party, the object itself, if it possesses any form of autonomous capability, operates with full knowledge of its own actions during perihelion. The other party, human civilization, attempting to characterize and understand the visitor, loses all observation capability during the most operationally significant phase of the encounter. This asymmetry exists whether the object is natural or artificial, but only matters strategically if intelligence guides the visitor's behavior. Natural comets do not exploit observational blind spots because they lack the capacity for exploitation. They sublime, fragment, or continue along ballistic trajectories according to physics alone. But an engineered system could theoretically recognize that perihelion passage through solar conjunction provides maximum operational flexibility with minimum detection risk. The geometry would not need to be deliberately planned. It emerges naturally from orbital mechanics. But recognizing and utilizing that geometry requires intelligence. So, we wait in uncertainty, unable to distinguish between a natural object following predictable physics and an artificial one executing pre-programmed activities under cover of solar glare. Before 3I/Atlas disappeared behind the Sun, astronomers assembled the most comprehensive dataset ever gathered for an interstellar visitor during its inbound approach. This collection of observations from flagship instruments and coordinated ground-based campaigns represents our baseline understanding of the object, the reference against which any post-perihelion changes will be measured. The quality and depth of these measurements far exceed what was possible for either 1I/Oumuamua or 2I/Borisov, the previous interstellar visitors that passed through our solar system with far less warning and preparation time. The James Webb Space Telescope provided the cornerstone of compositional analysis through near-infrared spectroscopy, obtained in late September 2025. These observations revealed carbon dioxide as the dominant volatile species in the coma, with a CO2 to water vapor ratio of approximately 8:1. This finding proved robust and repeatable across multiple observation epochs, establishing beyond reasonable doubt that 3I/Atlas differs dramatically from typical solar system comets, where water usually dominates the volatile budget. The carbon dioxide dominance suggests formation beyond the CO2 ice line in the object's birth stellar system, or, alternatively, surface processing by cosmic rays over geological timescales that preferentially removed hydrogen-rich compounds. The Hubble Space Telescope captured morphological details through visible light imaging during mid-September, revealing the unusual sunward anti-tail that extends preferentially toward the Sun, rather than away from it. This elongated structure measured approximately 10 times longer than its width, creating a needle-like appearance in processed images. Modeling attributed the geometry to anisotropic outgassing from the sun-facing hemisphere, combined with viewing angle effects, but the extreme aspect ratio pushed against typical cometary behavior patterns, even while remaining within the envelope of natural explanations. Ground-based spectroscopy from multiple observatories detected neutral nickel emission lines across a range of heliocentric distances from approximately 3 astronomical units inward to 2 astronomical units. These observations expanded the growing census of metal-bearing comets, a phenomenon only recently recognized in the astronomical literature. What made 3 I/Atlas noteworthy was the apparent absence or weakness of iron emission lines that normally accompany nickel in cometary spectra. The nickel to iron ratio appeared anomalously high compared to cosmic abundance patterns, though interpretation of these measurements remained contested within the professional community. Polarimetry measurements placed 3 I/Atlas outside the parameter space occupied by known solar system comet families. The polarization of scattered sunlight depends sensitively on dust grain size, shape, and composition, making it a powerful diagnostic of coma properties. The fact that 3 I/Atlas exhibited polarization behavior distinct from hundreds of previously characterized comets suggested either unusual dust properties or a grain population we had not encountered before in natural objects. These measurements did not prove artificial origin, but they did demonstrate that the object differed measurably from the reference sample of solar system comets used to establish baseline expectations. Brightness measurements through October tracked steady increase as solar heating intensified during approach to perihelion. The absolute magnitude, a standardized measure of intrinsic brightness, implied a nucleus diameter somewhere between several hundred meters and several kilometers, depending on assumptions about surface reflectivity. This large uncertainty reflected the difficulty of distinguishing reflected sunlight from the nucleus versus scattered light from the surrounding coma. Only resolved imaging could separate these contributions definitively, and no telescope achieved sufficient resolution from Earth's distance. This dataset, comprehensive as it appears, still leaves fundamental questions unanswered. We know the object is carbon dioxide rich, morphologically unusual, possibly nickel-enriched and polarimetrically distinct. We do not know whether these properties result from exotic but natural formation conditions, or indicate something fundamentally different from a comet. The perihelion passage now happening behind the Sun could provide the thermal stress test that distinguishes between these possibilities, but we cannot watch it occur. Astronomers can predict with reasonable confidence how bright 3 I/Atlas should become at perihelion, based on established physics and observations of similar objects at comparable solar distances. These predictions form testable hypotheses, expectations that reality will either confirm or violate when the object emerges from behind the Sun in December. The brightness curve, a graph plotting apparent magnitude against time or heliocentric distance, encodes fundamental information about how aggressively the object responds to solar heating and how much surface area actively sublimates volatiles. At its discovery in early July 2025, 3 I/Atlas appeared at approximately magnitude 15, faint enough to require large telescopes and sensitive detectors for detection. As the object moved sunward through August and September, brightness increased steadily, following a power law relationship typical of comets. By late October, just before disappearing into solar conjunction, the object had brightened to roughly magnitude 10, visible through amateur telescopes, but still too faint for naked eye observation. The rate of brightening, quantified by astronomers as the slope of magnitude versus heliocentric distance on a logarithmic plot, fell within the range exhibited by active comets with vigorous outgassing. Extrapolating this trend forward predicts that 3 I/Atlas should reach peak brightness around magnitude 8 or 9 at perihelion on October 29th. For comparison, magnitude 6 represents the threshold of naked eye visibility under dark skies, while magnitude 0 matches the brightness of the star Vega. Magnitude 8 places the object well within reach of binoculars and small telescopes, bright enough for widespread amateur observation, if not for the unfortunate geometry placing it behind the sun. The predicted peak brightness suggests a nucleus several kilometers across, with active sublimation across much of the sunward hemisphere, assuming typical cometary albedo around 4%. But predictions carry uncertainty. If 3 I/Atlas has higher reflectivity than assumed, the same observed brightness could result from a smaller nucleus with more reflective surface properties. Alternatively, if the object consists of unusually dark material with very low albedo, the nucleus might be larger than estimates suggest. The brightness also depends on how efficiently solar heating drives outgassing and dust production. Some comets show explosive increases in activity as they approach perihelion, brightening faster than smooth extrapolation would predict. Others plateau or even fade if their volatile reserves become depleted, or if active regions shut down due to dust mantling. Historical examples provide context for the range of possibilities. Comet Ison in 2013 was predicted to become spectacularly bright at its extremely close perihelion passage, potentially visible during daytime. Instead, it fragmented and largely vaporized under intense solar heating, disappointing observers who had anticipated a great comet. Comet Lovejoy in 2011 survived a similarly close perihelion passage and emerged as a brilliant naked eye object, exceeding predictions. These cases demonstrate that comets can surprise astronomers in both directions, proving more fragile or more robust than models suggest. For 3 I/Atlas, the brightness prediction matters because it sets expectations for what we should see when the object reappears in late November or early December. If the object emerges at the predicted brightness, gradually fading as it moves outbound from perihelion, that behavior confirms it survived perihelion passage intact and continued sublimating predictably. If it appears significantly brighter than expected, that might indicate an outburst or fragmentation event that exposed fresh, volatile, rich material. If it appears much fainter or fails to reappear at all, that could mean structural failure and dispersal during perihelion passage. The prediction transforms an observational gap into a falsifiable hypothesis. We cannot watch what happens at perihelion, but we can calculate what should result from different scenarios and then test those calculations against reality when observations become possible again. The brightness curve becomes a diagnostic tool, encoding information about events we could not directly witness. The physics of comet outgassing at perihelion follows well-established thermodynamic principles, allowing scientists to model what should be happening to 3I/Atlas, even though direct observation remains impossible. These models convert solar flux into surface temperature into sublimation rates, and sublimation rates into observable phenomena like coma brightness and spectroscopic signatures. The predictions are only as good as the assumptions about composition and structure, but they provide a framework for understanding the invisible transformation occurring behind the sun. Solar heating intensity at 1.36 astronomical units delivers approximately 540 watts per square meter to a surface perpendicular to the sun's rays. This energy flux drives surface temperatures on the sunward hemisphere to somewhere between 200 and 300 Kelvin, depending on the object's albedo and thermal inertia. These temperatures sit well above the sublimation point for carbon dioxide ice at the near vacuum pressures surrounding the nucleus, explaining why JWST detected such vigorous CO2 emission even at greater distances before perihelion. Carbon dioxide sublimation follows an exponential relationship with temperature, meaning that small increases in surface heating produce disproportionately large increases in outgassing rate. At perihelion, the carbon dioxide sublimation rate should reach its maximum value, potentially releasing thousands of kilograms of gas per second if the nucleus measures several kilometers across and maintains substantial exposed ice areas. This gas escapes at speeds around several hundred meters per second, expanding outward to form the extended coma that scatters sunlight and creates the object's visible appearance. The gas does not travel alone. Dust grains embedded in the ice matrix get dragged along by the escaping gas, accelerated to velocities that allow them to overcome the nucleus's weak gravity. The dust-to-gas mass ratio, a critical parameter in comet models, determines how much solid material enters the coma versus how much gas evaporates cleanly. Higher dust production creates brighter comae because solid particles scatter sunlight more efficiently than transparent gas molecules. The sunward anti-tail observed by Hubble before perihelion suggests significant dust production, indicating that 3I/Atlas releases substantial solid material along with its carbon dioxide gas. Water ice sublimates more slowly than carbon dioxide at the same temperature because water molecules require more energy to break free from the ice lattice. At perihelion temperatures, water ice on the surface should begin contributing measurably to the coma, though still remaining subordinate to carbon dioxide, as JWST measurements indicated at larger distances. The water to carbon dioxide ratio might shift during perihelion as surface layers erode away and expose subsurface materials with potentially different compositions. More exotic volatiles could emerge during peak heating if they exist within the nucleus. Ammonia ice, carbon monoxide ice, methane ice, and complex organic molecules all have sublimation temperatures that might be reached only at perihelion. Spectroscopic detection of new emission lines that were absent in pre-perihelion observations would indicate that thermal processing exposed previously hidden materials, providing direct evidence of compositional stratification within the nucleus. The models also predict structural consequences of intense outgassing. Gas escaping preferentially from the sunward hemisphere creates reaction forces that act like tiny rocket thrusters, potentially altering the object's rotation state or trajectory through non-gravitational acceleration. If outgassing becomes too vigorous, the mechanical stress from gas pressure building beneath surface layers can fracture the nucleus, leading to splitting or catastrophic disruption. Comet nuclei are not solid rocks, but rather loosely consolidated aggregates of ice and dust that can fail structurally under thermal stress. All of these predictions describe what should be happening right now behind the Sun. Processes that will leave detectable signatures in the object's appearance and behavior when it emerges in December. The models give us expectations, hypotheses about the transformation occurring beyond our view. NASA's Deep Space Network represents one of the most powerful tracking and communication systems ever built, capable of detecting radio signals from spacecraft billions of kilometers away, and measuring velocities with centimeter per second precision through Doppler shift analysis. The network consists of 3 massive antenna complexes strategically positioned around Earth in California, Spain, and Australia, ensuring continuous coverage as our planet rotates. These facilities routinely track interplanetary missions, maintain contact with distant probes, and occasionally conduct radar observations of asteroids and comets that pass within range. The Deep Space Network could theoretically track 3 I/Atlas through portions of its perihelion passage, despite solar conjunction challenges. Radar observations, which actively transmit radio waves toward a target and measure the reflected echo, can sometimes penetrate closer to the Sun than passive optical observations, because radio wavelengths are less affected by scattered solar light. The technique requires the target to be bright enough in radar terms, meaning it must have sufficient size and reflectivity to return a detectable echo. For a nucleus, potentially several kilometers across, the radar cross-section might be adequate for detection even at perihelion distance. Yet no public announcements have indicated Deep Space Network tasking for 3 I/Atlas observations. The network's scheduling information, partially available through NASA's Eyes on the Solar System visualization tool, shows routine tracking of active missions like Voyager, New Horizons, and various Mars orbiters, but does not list specific observation campaigns for the interstellar visitor. This absence could mean several things, none of them individually conclusive, but collectively raising questions about priorities and information flow. The most straightforward explanation invokes resource constraints and mission priorities. Deep space network time is precious, allocated primarily to active spacecraft requiring communication for navigation, data downlink, or command uplink. Dedicated tracking of a natural object like a comet represents a lower priority use of resources that could instead support missions where communication windows are critical. The network operates near capacity most of the time, with multiple missions competing for antenna access. Scheduling additional observations for 3 I/Atlas would require bumping other activities or finding gaps in the timeline that might not exist during the perihelion window. Alternatively, radar observations may have been attempted but failed to detect a return signal strong enough for analysis. Not all objects make good radar targets. A highly porous nucleus with low bulk density might absorb, rather than reflect radio waves, producing weak or undetectable echoes. An irregular shape tumbling chaotically could direct reflected energy away from Earth most of the time, making detection difficult. Surface properties matter enormously for radar cross-section, with icy compositions generally reflecting less efficiently than rocky or metallic materials. A null detection would not necessarily be publicized, especially if the observation was conducted as a low-priority engineering test rather than a funded science investigation. A third possibility, more speculative but worth stating explicitly, considers that deep space network observations occurred but remain undisclosed. Certain types of tracking data, particularly precise velocity measurements that would reveal non-gravitational accelerations or trajectory changes, might be held in restricted channels if they showed results sufficiently anomalous to warrant careful internal review before public release. This does not require conspiracy, merely institutional caution in the face of potentially paradigm-challenging observations. If radar tracking detected behavior inconsistent with a natural comet, such as structured acceleration profiles or unexpected radar cross-section variations, agencies might reasonably choose to triple-check their analysis before making announcements that would generate intense scrutiny. The silence from Deep Space Network regarding 3I/Atlas leaves us wondering whether the capability exists but wasn't used, was used but failed, or succeeded, but produced results not yet ready for public discussion. Each scenario has precedent in the history of space operations. The last confirmed observations of 3I/Atlas before it disappeared into solar conjunction came from ground-based observatories in late October 2025, capturing the object during its final days of visibility as it approached the exclusion zone boundary. These images and spectra represent the most recent verified measurements, the endpoint of our continuous monitoring that began at discovery in July. Everything we learn after perihelion will be compared against this baseline to detect changes driven by peak solar heating. Amateur astronomers with moderate-sized telescopes contributed some of the final observations, posting images to online forums and social media showing the brightening coma as 3I/Atlas intensified its activity. These images revealed a diffuse glow centered on the nuclear region with the characteristic sunward anti-tail extension that Hubble had documented weeks earlier. The morphology remained consistent with pre-perihelion predictions, showing no dramatic outbursts or fragmentations that would signal structural instability. The steady brightening followed the expected power law relationship, suggesting that outgassing responded predictably to increasing solar flux without any sudden transitions. Professional observatories maintained spectroscopic monitoring through late October, tracking emission lines from various molecular species as solar heating liberated volatiles from the nucleus. The carbon dioxide emission that JWST had characterized as dominant remained strong and clearly detectable through ground-based instruments, despite the increasing solar separation that degraded observing conditions. Some facilities reported possible detections of additional species, including cyanogen, a molecule that produces characteristic blue-green emission and commonly appears in active comets. The neutral nickel emission that had generated controversy in earlier observations remained present, according to some reports, though signal-to-noise ratios degraded as the object moved closer to solar glare. Color measurements from the final observations showed the object maintaining a neutral to slightly reddish appearance in integrated light, consistent with scattered sunlight from dust grains in the coma. No reports emerged of the blue coloration that had appeared in the controversial Mars surface image from early October, suggesting that either the blue smudge was indeed a processing artifact, or that viewing geometry from Earth differed sufficiently from the Mars perspective to produce different color signatures. The dust production rate inferred from brightness and colour remained robust, indicating that 3I/Atlas continued, shedding significant solid material along with gas. Light curve measurements through late October tracked the expected brightening trend with no anomalous variations that would indicate rotational modulation or discrete outburst events. The smooth light curve suggested either that the nucleus rotates slowly enough that activity variations average out over observation timescales, or that outgassing occurs relatively uniformly across the sunward hemisphere rather than from discrete jets. This behavior differs from many solar system comets that show pronounced brightness variations correlated with rotation periods ranging from hours to days. The final astrometric positions, measurements of 3I/Atlas's location against background stars, allowed orbit refinement to high precision. These measurements confirmed the hyperbolic trajectory with excess velocity, proving interstellar origin beyond any reasonable doubt. The orbital elements showed no detectable non-gravitational acceleration beyond what models predicted from asymmetric outgassing, though measurement uncertainties left room for small effects below detection thresholds. More precise tracking after perihelion will test whether the close solar passage induced any trajectory changes. By November 1st, 3I/Atlas had moved too close to the Sun for safe observation from ground-based facilities. The last images showed a brightening object apparently healthy and active, following predicted behavior without obvious anomalies. Then it vanished into the glare, beginning a 6-week absence, during which its most dramatic transformation would occur unseen. The final pre-conjunction observations became historical record, a snapshot of the object's state before perihelion altered everything we thought we knew about its nature. While Earth-based telescopes and near-Earth space observatories lose all capability to track 3I/Atlas during solar conjunction, a handful of specialized spacecraft occupy positions that might allow observations from angles Earth cannot access. These assets, designed primarily for solar monitoring or positioned elsewhere in the solar system, represent the only potential sources of data during the perihelion blackout period. Whether they actually observed the interstellar visitor depends on mission priorities, scheduling constraints, and whether observation campaigns were planned in advance. The Solar and Heliospheric Observatory, known as SOHO, orbits the first Lagrange point between Earth and Sun, where gravitational forces balance to maintain a stable position. This spacecraft carries coronagraph instruments specifically designed to block direct sunlight while imaging the extended solar corona. The LASCO coronagraphs create artificial eclipses, allowing cameras to photograph faint structures near the Sun that would otherwise be overwhelmed by solar glare. These instruments have discovered thousands of comets over SOHO's decades of operation, most of them small sun grazers that pass extremely close to the solar surface before vaporizing. SOHO's outermost coronagraph, designated C3, images the corona from approximately 4 to 30 solar radii from the Sun's center. At perihelion, 3I/Atlas sits at 1.36 astronomical units, which converts to roughly 290 solar radii from the Sun's center. This places the object far beyond SOHO's normal field of view, well outside the region where coronagraph imaging remains sensitive to faint sources. However, if 3I/Atlas underwent a massive brightening event, or released an exceptionally large amount of dust, scattered light from the extended coma might become detectable even at that distance. SOHO data archives are publicly accessible with minimal delay, allowing anyone to search for anomalous features appearing during the perihelion window. The Parker Solar Probe represents a more intriguing possibility. This spacecraft follows a highly elliptical orbit that brings it closer to the Sun than any previous mission, diving through the solar corona to study magnetic fields and plasma physics. Parker's trajectory takes it to varying solar distances throughout its mission, with closest approaches occurring every few months as it completes each orbit. The probe's position during late October and early November 2025 determines whether it could observe 3 I/Atlas from a vantage point significantly different from Earth's perspective. If Parker happened to be positioned away from the Earth-Sun line during perihelion, it might observe 3 I/Atlas at a solar separation angle large enough for detection, despite being in conjunction from Earth's view. The spacecraft carries imaging instruments designed to study the solar wind and corona, not faint comets, but those instruments might detect a bright enough object passing through their fields of view. Parker data, however, typically undergo extensive processing before public release, and the spacecraft's primary mission focuses entirely on solar physics rather than tracking transient interstellar visitors. The stereo spacecraft, designed to observe the Sun from locations offset from the Earth-Sun line, could theoretically provide observations during solar conjunction if both spacecraft remain operational. These twin probes were launched to create a stereoscopic view of solar activity, positioned ahead of and behind Earth in its orbit. From these offset vantage points, objects in solar conjunction, as seen from Earth, might be observable at larger angular separations from the solar disk. However, stereo mission status and data availability during the critical perihelion window would determine whether useful observations occurred. These assets represent long shots rather than guaranteed observation platforms. They were not designed for comet tracking, may not have been pointed at 3 I/Atlas, even if geometry allowed observation, and operate with data release schedules that might delay any findings for weeks or months. Still, they represent the only options for breaking the observational blackout during perihelion. The Solar and Heliospheric Observatory has been watching the Sun continuously since 1996, positioning itself at the first Lagrange point, approximately 1.5 million kilometers from Earth in the direction of the Sun. From this gravitationally stable location, SOHO maintains an uninterrupted view of our star, monitoring solar activity through multiple instruments that span wavelengths from ultraviolet to visible light. Among these instruments, the Large Angle and Spectrometric Coronagraph experiment, abbreviated as LASCO, has achieved unexpected fame for discovering comets that were never its primary targets. LASCO consists of 3 separate coronagraphs designated C1, C2, and C3, each designed to image different regions of the solar corona by creating artificial eclipses. An occulting disk blocks the overwhelmingly bright solar photosphere, allowing cameras to photograph the much fainter extended atmosphere surrounding the Sun. The C3 coronagraph, the outermost of the 3, images from approximately 4 solar radii out to 30 solar radii from the Sun's center. This field of view has captured more than 4,000 comets over SOHO's operational lifetime, most of them discovered by amateur astronomers scrutinizing publicly available LASCO images posted online within hours of acquisition. These SOHO comets fall predominantly into the Kreutz Sungrazer family, objects following extremely close approaches that bring them within a few solar radii of the surface before intense heating vaporizes them completely. The comets appear as moving bright spots against the dark background of space surrounding the occulted solar disk, their motion detectable across consecutive images taken minutes or hours apart. Some survive their perihelion passage and emerge on the other side of the Sun, while others simply fade from view as thermal destruction overwhelms their structural integrity. 3. I/Atlas at perihelion sits at 1.36 astronomical units from the Sun, a distance that translates to roughly 290 solar radii. This places the object approximately 10 times farther from the Sun than the outer edge of LASCO C3's normal field of view. At such distances, the coronagraph was never designed to detect faint objects, and sensitivity falls off dramatically beyond the nominal imaging range. For 3 I/Atlas to appear in SOHO data, it would need to become extraordinarily bright, orders of magnitude more luminous than predictions based on pre-perihelion observations suggested. But extraordinary brightening is not impossible for comets at perihelion. Outburst events, where sudden exposure of fresh volatile rich material drives explosive increases in gas and dust production, can boost brightness by factors of 10 or even 100 in a matter of hours. Fragmentation events similarly release vast amounts of material, as structural breakup exposes interior ices to direct solar heating. If 3 I/Atlas underwent such a catastrophic event during its perihelion passage, the resulting dust cloud might scatter enough sunlight to become detectable even at its great distance from SOHO's primary field of view. The LASCO data archives are publicly accessible through NASA's SOHO website, with new images posted continuously as they downlink from the spacecraft. Anyone with internet access can browse through recent observations, looking for anomalous features or unexpected bright spots that might correspond to 3 I/Atlas during the perihelion window. The amateur comet hunting community that has discovered thousands of SOHO comets over the years could potentially spot the interstellar visitor if it brightened sufficiently, though the distance and faintness make detection highly unlikely under normal circumstances. No reports have emerged as of early November 2025 of 3 I/Atlas detections in SOHO coronagraph data. This non-detection tells us something important. It means the object did not undergo a catastrophic brightness increase large enough to become visible from SOHO's vantage point. The perihelion passage, whatever it entailed, occurred without explosive outbursts or fragmentations that would flood the inner solar system with detectable dust. This suggests either successful structural survival or changes too subtle to produce the massive brightness spike required for SOHO visibility. NASA's Parker Solar Probe represents humanity's most ambitious attempt to touch the Sun, diving repeatedly through the outermost layers of the solar atmosphere on a mission to understand the physics of stellar corona and solar wind acceleration. Launched in 2018, the spacecraft follows a highly eccentric orbit that brings it progressively closer to the Sun with each pass, using Venus gravity assists to tighten its trajectory over the course of multiple years. By late 2025, Parker routinely ventures inside 10 solar radii from the solar surface, far closer than any previous spacecraft has survived. The extreme proximity to the Sun requires extraordinary engineering. A carbon composite heat shield nearly 12 centimeters thick protects the spacecraft's instruments from temperatures exceeding 1,400 degrees Celsius on the sun-facing side. Behind this shield, the spacecraft bus maintains near room temperature, allowing sensitive electronics and scientific instruments to operate normally despite the infernal environment just meters away. The thermal protection system does not cool the spacecraft actively. Instead, it simply blocks thermal radiation and reflects incident sunlight, while allowing heat to radiate from the shadowed side into cold space. Parker's scientific payload focuses entirely on solar physics, carrying instruments to measure magnetic fields, plasma properties, and energetic particles in the corona. The Wide Field Imager for Solar Probe, designated WISPR, represents the only optical imaging system aboard the spacecraft. WISPR consists of two telescopes pointing perpendicular to the heat shield, imaging the solar wind and corona from perspectives impossible to achieve from Earth or Earth orbit. The instrument was designed to track solar wind structures and capture images of the Sun's atmosphere, not to search for faint comets or interstellar visitors passing through the inner solar system. Nevertheless, WISPR has captured fortuitous observations of various celestial objects during Parker's mission. The cameras have photographed Venus during close flybys, imaged dust structures in the zodiacal cloud, and even glimpsed Earth and other planets from their unique vantage point near the Sun. If 3I/Atlas passed through WISPR's field of view during the perihelion window, and if the object was bright enough to stand out against background zodiacal light and instrumental noise, the cameras would record its presence, regardless of whether anyone was specifically looking for it. The critical question becomes Parker's orbital position during late October and early November 2025. Parker's trajectory brings it to perihelion, its closest solar approach, approximately every 3 months as it completes each elliptical orbit. Between these close passes, the spacecraft swings back out to distances comparable to Venus's orbit before falling inward again. If Parker happened to be near its own perihelion during the same time frame as 3I/Atlas, the spacecraft might observe the interstellar visitor from a vantage point relatively close to the Sun, possibly at an angle that placed the object outside the solar exclusion zone, as seen from Parker's perspective. Alternatively, if Parker was near aphelion, far from the Sun on the outbound leg of its orbit, it would share Earth's viewing geometry and face the same observational constraints. The spacecraft's position follows a predetermined trajectory calculated years in advance, making it straightforward to determine whether favorable geometry existed. However, even if geometry allowed observation, WISPR would need to be pointed in the right direction at the right time, a circumstance that depends on spacecraft attitude planning, unrelated to 3I/Atlas. Parker Solar Probe data undergo extensive processing and calibration before public release, typically with delays measured in months rather than days. If WISPR captured images of 3I/Atlas during perihelion passage, those data might not appear in public archives until well after the object has emerged from solar conjunction and been reacquired by Earth-based observatories. The Parker window represents a possible but uncertain source of perihelion observations that might eventually shed light on what happened during the blackout. Beyond professional space-based assets like SOHO and Parker Solar Probe, a distributed network of amateur solar observers operates coronagraph equipment from locations around the world, creating a continuous monitoring capability that complements official missions. These amateur instruments, while less sophisticated than billion-dollar spacecraft, collectively provide observational coverage that professional facilities sometimes cannot match due to scheduling constraints or data release delays. The amateur coronagraph community has proven its value repeatedly through discoveries of bright comets and solar phenomena that might otherwise have gone unnoticed. Modern amateur coronagraphs utilize relatively simple optical designs based on principles established more than a century ago. An occulting disc mounted in front of the telescope objective blocks direct sunlight from reaching the detector, creating an artificial eclipse that allows much fainter structures near the sun to become visible. Careful baffling and light trapping minimize scattered light inside the instrument, improving contrast between the dark sky and faint coronal features or passing comets. Digital cameras adapted from commercial astrophotography equipment provide sensitive detection, while automated tracking systems maintain precise pointing toward the sun throughout daylight hours. These instruments typically achieve fields of view extending from approximately 2 to 10 solar radii from the sun's center, overlapping with SOHO's LASCO C2 and C3 coronagraphs, but operating independently from ground-based locations. The advantage of ground-based observation comes from continuous monitoring, limited only by weather and local night-day cycles. While SOHO observes from its constant position at the Earth-Sun Lagrange point, amateur observers distributed across multiple continents ensure that at least some locations maintain solar visibility at any given time. The Amateur Coronagraph Network has discovered numerous sun-grazing comets, small icy bodies that pass within a few solar radii of the surface before vaporizing completely. These discoveries often occur through visual inspection of images posted to online forums and social media, where observers share their data in near real time. The community has developed expertise in distinguishing genuine comets from instrumental artifacts, cosmic ray hits, and various forms of noise that can masquerade as astronomical sources in coronagraph images. This collective experience makes the network remarkably effective at identifying unusual features that merit further investigation. For 3 I/Atlas at perihelion, amateur coronagraphs face the same fundamental limitation as SOHO. The object's distance of 1.36 astronomical units, nearly 300 solar radii from the sun's center, places it far beyond the typical imaging range of ground-based coronagraph equipment. Detection would require the interstellar visitor to undergo extraordinary brightening, orders of magnitude beyond normal cometary behavior, to become visible at such distances. The scattered light from an enormous dust cloud or catastrophic fragmentation event might potentially reach detectable levels, but nominal perihelion activity would remain far too faint. No reports have emerged from the amateur coronagraph community of 3 I/Atlas detections during late October or early November 2025. The absence of sightings corroborates the lack of SOHO detections, strengthening the conclusion that perihelion passage occurred without massive outbursts or structural failures. This non-detection actually provides useful information. It constrains how dramatically the object's behavior could have changed during the observational blackout. Any scenario involving explosive brightening or catastrophic breakup would likely have produced detectable signatures even at the object's great distance from the sun. The amateur network remains vigilant, continuing to monitor the solar environment through November as 3 I/Atlas presumably moves outbound from perihelion. If delayed brightening occurs, perhaps triggered by exposure of subsurface materials, days or weeks after peak heating, amateur observers might spot the first signs of unusual activity before professional facilities reacquire the target. The distributed nature of amateur observation networks means that someone, somewhere, is always watching the sky around the Sun. The most straightforward explanation for what 3I/Atlas is experiencing during perihelion invokes well-established comet physics operating at maximum intensity. This scenario requires no exotic processes, no unusual materials, and no departures from how natural icy bodies respond to solar heating. It simply extrapolates the carbon dioxide-dominated outgassing that JWST observed at larger distances and predicts how that activity intensifies as solar flux peaks at closest approach. At 1.36 astronomical units, surface temperatures on the sunward hemisphere should reach approximately 250 to 300 Kelvin, depending on the nucleus's thermal properties. These temperatures drive carbon dioxide sublimation rates to their maximum values, releasing gas at speeds near 400 meters per second as molecules escape from the ice lattice and accelerate away from the weak gravity of a nucleus measuring just a few kilometers across. The gas flux, measured in kilograms per second, scales exponentially with temperature, meaning that the relatively modest temperature increase from pre-perihelion conditions produces disproportionately large increases in outgassing intensity. The carbon dioxide to water ratio observed earlier by JWST at 8:1 should remain approximately constant through perihelion, though water ice contribution might increase slightly as surface erosion exposes deeper layers where water content could differ from the surface composition. Both volatiles sublime vigorously at perihelion temperatures, creating a dense inner coma that extends outward for thousands of kilometers before thinning into the more diffuse extended envelope mapped by spherex at greater distances. The total gas production rate for a nucleus several kilometers across could reach 10,000 kilograms per second or higher, comparable to highly active solar system comets at similar heliocentric distances. Dust production accompanies gas release as escaping volatiles drag along solid particles embedded in the ice. The dust-to-gas mass ratio, a parameter that varies widely among comets depending on composition and structure, determines how much solid material enters the coma. 3I/Atlas showed robust dust production before perihelion based on its brightness and the visible anti-tail structure captured by Hubble. At perihelion, dust production should intensify proportionally with gas output, potentially filling the inner solar system with fine particles that scatter sunlight efficiently and contribute to the object's integrated brightness. The sunward anti-tail morphology observed earlier should persist or even strengthen during perihelion, as anisotropic outgassing from the sun-facing hemisphere continues directing material preferentially toward the sun. Models attribute this geometry to differential heating between the day side and night side of the nucleus, combined with favorable viewing angles that emphasize the sunward component of the dust distribution. Nothing in this explanation requires departure from natural comet behavior, though the extreme aspect ratio, measuring 10:1, remains somewhat unusual compared to typical comets. Spectroscopic signatures should show peak intensities for all previously detected species. Carbon dioxide emission lines will brighten. Neutral nickel emission, if real, should strengthen. And water vapor lines will become more prominent as water ice sublimation increases. New emission features might appear if volatile species with higher sublimation temperatures exist within the nucleus and only emerge under peak heating. Cyanogen, ammonia, carbon monoxide, and various organic molecules all have characteristic spectral signatures that would become detectable if present in sufficient quantities. Structural integrity should hold under this scenario. The modest solar heating at 1.36 astronomical units, while intense enough to drive vigorous outgassing, remains well below the levels that typically fracture comet nuclei. Objects survive perihelion passages at these distances, routinely without fragmenting, though occasional cases of splitting do occur when internal stresses exceed the tensile strength of loosely consolidated ice and dust aggregates. 3. I/Atlas should emerge from perihelion intact, its brightness declining gradually as it moves outbound and solar heating decreases, following a light curve that mirrors the inbound, brightening with minor asymmetries resulting from seasonal effects and surface evolution. This scenario predicts a successful perihelion passage with no dramatic surprises, an interstellar comet behaving exactly as exotic, but natural icy bodies should behave when approaching the Sun. Comet nuclei are not solid monolithic rocks, but rather fragile aggregates of ice, dust, and rocky material bound together by frozen volatiles acting as cement. When solar heating intensifies during perihelion approach, thermal stress can exceed the structural strength of these loosely consolidated bodies, triggering fragmentation events that transform a single object into multiple pieces or complete dispersal into expanding clouds of debris. History provides numerous examples of comets that failed to survive their closest solar approach, offering cautionary precedents for what might have happened to 3 I/Atlas behind the Sun. Comet Linear, formerly designated C2000WM1, disintegrated spectacularly in July 2000 as it approached perihelion at approximately 0.77 astronomical units from the Sun. Observers watched the nucleus split into multiple fragments over the course of several days, each piece developing its own small coma as exposed ice sublimated from freshly created surfaces. The fragmentation process released vast amounts of dust and gas that had been locked inside the original nucleus, producing a temporary brightness surge as the breakup exposed volatile rich materials directly to solar heating. Within weeks, the fragments dispersed completely, and the comet effectively ceased to exist as a coherent object. Comet Elenin in 2011 followed a similar trajectory toward destruction. As it approached perihelion at approximately 0.48 astronomical units, the nucleus fragmented and dispersed, fading rapidly from view as the pieces spread apart and sublimated away. Ground-based observers documented the disintegration through progressively fainter images showing elongated structures rather than compact nuclei, characteristic signatures of ongoing breakup. The comet never recovered from this structural failure, disappearing entirely rather than emerging intact on an outbound trajectory. The physics underlying these failures involves thermal gradients, internal pressure, and mechanical stresses that develop as surface layers heat, while interior regions remain cold. Gas generated by sublimating ice cannot always escape freely through overlying dust mantles, building pressure beneath the surface like steam in a sealed container. When pressure exceeds the tensile strength holding the nucleus together, fractures propagate through the structure, splitting the object along lines of weakness. Once fragmentation begins, it often accelerates as newly exposed surfaces sublime rapidly under direct solar illumination. For 3I/Atlas, perihelion at 1.36 astronomical units delivers less intense heating than the distances where linear and Lenin fragmented, suggesting lower structural stress and better survival odds. However, interstellar objects might possess different mechanical properties than solar system comets. Material that formed in another stellar system and spent millions or billions of years in interstellar space could have different ice crystallinity, dust grain cohesion, or internal structure compared to objects that formed locally. Cosmic ray bombardment and micrometeoroid impacts during the long interstellar journey might have weakened structural integrity, creating fracture planes that fail under thermal stress that local comets would survive. If 3I/Atlas underwent structural failure during perihelion, the signatures would be diagnostic and unmistakable. The object would fragment into multiple condensations, each generating its own coma as exposed ice sublimated. Total brightness might spike temporarily as breakup released internal volatiles, then fade rapidly as the fragments dispersed and depleted their volatile reserves. Spectroscopy would show broadened emission lines, reflecting the range of velocities among separating pieces. Long-term tracking would reveal multiple trajectories diverging from the original orbit as fragments acquired different velocities during the breakup process. The consequences for observation depend on timing. If fragmentation occurred early during perihelion passage, the debris cloud might disperse substantially before emerging from solar conjunction, making reacquisition difficult or impossible. If structural failure happens late, near the end of the blackout period, fragments might remain concentrated enough for detection when they reappear in observable sky. Either way, 3I/Atlas as a single coherent object would cease to exist, replaced by a spreading collection of smaller pieces, gradually fading into undetectability. If 3I/Atlas represents something other than a natural comet, perihelion offers the ideal moment for systems activation after a potentially dormant cruise through interstellar space, lasting thousands or millions of years. This scenario, clearly speculative, but grounded in engineering logic, considers what an artificial probe would need to do when encountering maximum available solar energy at closest approach to a star. The physics of spacecraft thermal management and power generation dictate specific behaviors that would distinguish engineered systems from natural ice sublimation. Solar power generation scales directly with available flux, reaching peak output when photovoltaic surfaces receive maximum illumination. At 1.36 astronomical units, solar irradiance delivers approximately 540 watts per square meter, roughly 40% of the intensity at Earth's orbit, but still substantial for power harvesting. A probe with even modest solar panel area, measuring tens of square meters, could generate kilowatts of electrical power, enough to operate communication systems, scientific instruments, attitude control mechanisms, and data processing equipment that might have been shut down or minimally powered during the long transit between stars. Thermal management becomes the critical engineering challenge near perihelion. Any structure absorbing solar radiation heats up until thermal emission balances incoming energy. For a dark surface with low reflectivity, equilibrium temperatures at 1.36 astronomical units would reach several hundred Kelvin, potentially damaging sensitive electronics or destabilizing structural materials. Engineered spacecraft manage this thermal load through multiple techniques, including reflective surfaces that minimize absorption, radiators that efficiently emit infrared radiation into cold space, and active cooling systems that transport heat from hot regions to radiator surfaces. One particularly effective thermal management strategy involves directional outgassing, deliberately releasing gas or sublimating expendable material, preferentially from the sun-facing hemisphere. The phase change from solid or liquid to gas absorbs substantial thermal energy, cooling the surface while the expelled material carries excess heat away from the structure. This mechanism operates identically to natural comet sublimation in its physics, but differs in purpose and control. An engineered system could modulate outgassing rates through active valves or variable surface exposure, maintaining internal temperatures within operational limits, regardless of varying solar flux. The observable signatures of thermal management activation would mimic natural comet behavior in many respects, making distinction difficult without detailed spectroscopy or high-resolution imaging. Both natural ice sublimation and engineered thermal control produce gas emission from sun-facing surfaces. Both create visible comas through scattered light, and both generate non-gravitational forces that slightly alter trajectories. The key differences emerge in the details, in symmetries or asymmetries of emission patterns, in spectroscopic signatures that might reveal industrial materials rather than natural ices, and in temporal variations that follow programmed control logic rather than passive thermal response. Carbon dioxide makes an excellent thermal management fluid for several reasons. Its sublimation temperature at low pressure matches the temperature regime near 1 astronomical unit from the Sun. It absorbs substantial energy during phase change, and it remains chemically inert with most structural materials. An engineered probe using carbon dioxide for thermal control would appear spectroscopically similar to a natural carbon dioxide-rich comet, potentially explaining the JWST observations that found CO2 dominating the coma composition. The 8:1 ratio relative to water could reflect deliberate design choices about volatile reserves, rather than formation conditions in a distant protoplanetary disk. If 3 I/Atlas activated thermal management systems at perihelion, the outgassing would intensify precisely as predicted for natural comets, making the scenarios observationally degenerate without additional diagnostic signatures. Brightness would increase due to expanding coma, spectroscopy would show expected molecular emissions, and morphology would display sunward concentration of activity. The engineered scenario differs primarily in intent rather than implementation, using the same physics for controlled purposes that nature employs passively. Detection would require finding asymmetries or modulations inconsistent with passive thermal response, subtle signatures that might only become apparent through careful comparison of pre- and post-perihelion observations. An alternative artificial scenario considers the possibility that 3 I/Atlas might deliberately minimize activity during perihelion, rather than activating systems or increasing operations. This hibernation strategy makes engineering sense for a probe designed to survive multiple stellar encounters over extremely long mission durations, measured in millions of years. Perihelion represents a period of maximum environmental stress when thermal loads peak, radiation exposure intensifies, and any mechanical systems face elevated risk of failure. A cautious design philosophy might favor dormancy during these high-risk phases, preserving capability for later mission stages when conditions improve. The engineering precedent comes from terrestrial spacecraft that routinely enter safe modes during anticipated hazardous events. When a solar storm threatens satellites with intense radiation, mission controllers sometimes shut down non-essential systems, orient the spacecraft to minimize exposure, and wait for conditions to improve before resuming normal operations. This protective posture reduces power consumption, limits heat generation, and prevents damage to sensitive electronics that might not survive the peak radiation environment. The same logic applies to perihelion passage, where thermal stress and particle flux from the solar wind reach maximum intensity. A hibernating probe would present minimal cross-section to solar radiation through orientation control, perhaps edge-on rather than broadside, to reduce absorbed energy. Surface coatings optimized for low solar absorptivity, but high infrared emissivity would minimize equilibrium temperature by reflecting incident sunlight while efficiently radiating away any absorbed heat. The structure might employ passive thermal control, relying on material properties rather than active systems that require power and introduce failure modes. Multi-layer insulation, similar to the blankets that protect satellites in Earth orbit, could isolate internal components from external temperature extremes. The observable signatures of hibernation would appear remarkably similar to a low-activity natural comet. Reduced or absent outgassing would produce a faint or non-existent coma, making the object difficult to detect visually, but potentially revealing through reflected sunlight from the nucleus itself. Spectroscopy might show minimal emission lines corresponding to low gas production rates. The morphology would lack the extended tail structures characteristic of active comets, presenting instead as a compact point source or slightly resolved disk, depending on observation, resolution, and distance. This scenario offers one explanation for why 3I/Atlas might not appear in SOHO coronagraph data or amateur observations during perihelion. If the object minimized its activity deliberately, reducing outgassing to near zero while maintaining a low albedo protective surface, it would remain far too faint for detection. At its distance of nearly 300 solar radii from SOHO's field of view, the hibernation state would mimic an inactive asteroid rather than an active comet, dramatically reducing scattered light signatures that make comets visible. The strategy assumes advanced mission planning capabilities and robust autonomous systems that can sense environmental conditions and adjust operational modes accordingly. The probe would need to monitor solar flux, internal temperatures, and system health, then execute pre-programmed responses when thresholds are exceeded. These capabilities exist in current terrestrial spacecraft, so extending them to an interstellar probe requires no physics breakthroughs, merely engineering refinement and reliability improvements to function over geological timescales. Distinguishing hibernation from natural low activity requires detecting subtle asymmetries or controlled behaviors that passive objects cannot exhibit. A natural comet with depleted volatiles or a thick dust mantle might also show minimal outgassing, making it observationally similar to a hibernating probe. The scenarios become separable through trajectory analysis if non-gravitational accelerations appear after perihelion, suggesting course corrections through brightness variations that follow patterns inconsistent with random tumbling, or through spectroscopic signatures that reveal materials incompatible with natural composition. The hibernation scenario predicts that 3 I/Atlas will reappear in observable sky during late November or December, showing reduced activity compared to pre-perihelion observations. The object might appear fainter than predicted, lacking the bright extended coma expected from peak outgassing. Spectroscopy might reveal changed emission line intensities, suggesting altered surface properties or depleted volatile reservoirs. These signatures would be consistent with either a natural comet that shut down activity after volatiles were exhausted, or an engineered probe that deliberately entered dormancy to survive perihelion stress. Separating these interpretations requires additional data. Beyond simple redetection, military and intelligence space assets operate in domains deliberately obscured from public view, conducting missions that remain classified for years or decades after their operational lifetimes conclude. The capability exists within multiple national space programs to track objects throughout the solar system using telescopes, radar systems, and specialized sensors that never appear in civilian catalogs or scientific publications. These classified assets, funded through compartmentalized budgets hidden within broader defense spending, could theoretically observe 3 I/Atlas during perihelion passage, even while civilian facilities remain blind due to solar conjunction geometry. The United States Space Force operates the Space Surveillance Network, a globally distributed system of ground-based radars and optical telescopes that track thousands of artificial satellites and debris objects in Earth orbit. While this network focuses primarily on near-Earth space, its most powerful radars can detect objects at lunar distances and beyond. Deep space tracking capabilities, derived from Cold War-era investments in monitoring distant spacecraft and potential threats, extend far beyond what civilian agencies publicly acknowledge. Similar capabilities exist within Russian, Chinese, and potentially other national space programs that maintain strategic awareness of activities throughout cislunar space and the inner solar system. Classified space telescopes represent another potential observation pathway. The National Reconnaissance Office, responsible for operating intelligence satellites, maintains optical imaging systems comparable to or exceeding Hubble Space Telescope capabilities, but pointed downward toward Earth's surface for reconnaissance purposes. Unacknowledged assets might exist with orientations allowing deep space observation, particularly if monitoring artificial satellites and potential threats from beyond Earth orbit serves strategic intelligence goals. The existence of such systems would remain classified indefinitely, with any observations of 3 I/Atlas during perihelion falling under operational security restrictions. The hypothesis that classified observations occurred gains circumstantial support from historical precedents, where military sensors detected events before civilian systems reported them publicly. Meteor entries, particularly those involving objects large enough to penetrate deep into the atmosphere, often appear first in classified data from sensors designed to detect nuclear detonations. The interstellar meteors designated IM-1 that Avi Loeb's team studied came from precisely such data, declassified years after the event, once strategic sensitivity diminished. 3 I/Atlas, if observed by military sensors during perihelion, might follow a similar trajectory toward eventual public disclosure, but remain hidden for years during initial classification review. The coordination challenges inherent in multinational space operations create natural compartmentalization. Even if United States assets observed 3 Sun I/Atlas during solar conjunction, those observations might not be shared with NASA or ESA due to classification restrictions on sensor capabilities, orbital parameters, or operational details. The data would exist in classified archives, accessible only to cleared personnel working on specific programs, preventing scientific analysis or public release, even if the observations themselves were scientifically valuable. This information asymmetry is not conspiracy, but standard operating procedure for military space activities. The implications of black budget observations depend entirely on what those hypothetical measurements revealed. If classified sensors tracked 3 I/Atlas through perihelion and detected behavior consistent with natural comet physics, the data would support mainstream interpretations, but remain hidden nonetheless due to classification of the observation platform rather than the results. If tracking revealed anomalous behavior, trajectory changes inconsistent with outgassing forces, or signatures suggesting artificial systems, classification would almost certainly tighten further under national security rationales. The black budget hypothesis is ultimately unfalsifiable in the near term. Classified observations either exist or do not, but outsiders cannot determine which case applies because the absence of public data could result from either non-observation or successful classification. This uncertainty creates a permanent question mark hanging over the perihelion blackout period. We cannot rule out the possibility that detailed tracking data exists somewhere in restricted archives, documenting exactly what 3 I/Atlas did during its closest solar approach, while civilian astronomers waited blindly for the object to reappear in observable sky. The mathematics of celestial mechanics allow precise calculation of when 3 I/Atlas will emerge from solar conjunction and become observable again from Earth. Orbital dynamics and the changing geometry between Earth, Sun, and the interstellar visitor dictate a timeline measured in weeks rather than months, with the object gradually increasing its angular separation from the Sun as both it and Earth continue moving along their respective paths. The reappearance will not occur suddenly, but rather as a gradual transition from unobservable to marginally detectable to clearly visible over the course of several weeks during late November and early December 2025. Angular separation represents the critical parameter determining observability. When 3 I/Atlas sits less than 30 degrees from the Sun as measured across the sky, solar glare overwhelms any attempt at observation from Earth-based telescopes or near-Earth spacecraft. As the object moves outbound from perihelion while Earth continues its annual orbit, the angular gap widens incrementally each day. By late November, separation should exceed 30 degrees, placing the object at the edge of the exclusion zone, where the most capable observatories might attempt detection despite challenging conditions. By early December, separation reaches 40 to 50 degrees, allowing routine observation by professional facilities equipped with appropriate instrumentation. The viewing geometry favors Southern Hemisphere observers during the initial reappearance window. 3 I/Atlas will emerge into morning sky as seen from southern latitudes, rising before dawn at increasingly earlier times as December progresses. Northern Hemisphere facilities face less favorable geometry, with the object remaining closer to the horizon and fighting both atmospheric extinction and twilight contamination. This geographic bias means that observatories in Chile, Australia, and South Africa will likely capture the first reacquisition images, with Northern Hemisphere facilities joining the campaign days or weeks later as geometry improves. Brightness at reappearance determines how quickly astronomers can re-establish tracking. If 3 I/Atlas emerges at predicted magnitude 9 or 10, large amateur telescopes and small professional instruments should detect it within days of reaching observable angular separation. If the object has faded significantly due to declining outgassing rates or structural changes during perihelion, detection might require larger apertures and longer integration times, delaying reacquisition by a week or more. If brightness has increased unexpectedly due to delayed outbursts or fresh material exposure, the object might become visible earlier than predictions suggest, appearing as soon as angular separation barely exceeds the exclusion zone threshold. The International Astronomical Union's Minor Planet Center coordinates global observation campaigns for unusual objects like 3 I/Atlas, collecting astrometric measurements from observatories worldwide and computing refined orbital solutions. As soon as any facility reports a confirmed detection, the Minor Planet Center will issue an electronic circular alerting the broader astronomical community and providing updated coordinates for follow-up observations. This coordination mechanism ensures rapid dissemination of reappearance information, allowing multiple independent facilities to confirm the detection and begin characterization measurements. December 19th, 2025 represents an optimal observation date when 3 I/Atlas reaches approximately 1.8 astronomical units from Earth, with favorable viewing geometry from both hemispheres. At this distance and configuration, the object should be readily observable through medium-sized telescopes if it has survived perihelion intact and maintains reasonable activity levels. This date becomes a natural checkpoint for assessing the visitor's post-perihelion state, comparing brightness, spectroscopy, and morphology against pre-perihelion baselines established in October. The reappearance timeline transforms abstract orbital mechanics into concrete observational opportunities. Astronomers worldwide are marking calendars, preparing instrumentation, and coordinating telescope time for late November and December. The waiting period tests patience and disciplines speculation, forcing attention back toward empirical measurement rather than theoretical scenarios. In a matter of weeks, 3 I/Atlas will either confirm expectations or deliver surprises that rewrite our understanding of what passed through the solar exclusion zone during the blackout. The timeline is set, the countdown has begun, and nothing remains but to watch the sky and wait for the interstellar visitor to reveal what perihelion made of it. The moment 3 I/Atlas reappears in observable sky, astronomers will immediately search for specific signatures that distinguish between the competing scenarios for what happened during perihelion. These diagnostic observables, ranging from simple brightness measurements to complex spectroscopic analysis, will either confirm that the object behaved as predicted for a natural comet, or reveal anomalies demanding exotic explanations. The first few nights of reacquisition observations will prove critical for establishing whether perihelion passage fundamentally altered the visitor's properties or left it essentially unchanged. Brightness comparison against pre-perihelion measurements provides the simplest diagnostic. If 3 I/Atlas emerges at magnitude 8 or 9 as predictions suggest, fading gradually as outgassing declines with increasing solar distance. That behavior indicates successful structural survival and continued normal sublimation of volatiles. If the object appears significantly brighter than expected, possibly magnitude 6 or 7, that could indicate an outburst during perihelion that released vast amounts of fresh material, or alternatively, a fragmentation event that exposed multiple surfaces to solar heating. If brightness falls far below predictions, appearing at magnitude 11 or fainter, that suggests either structural failure that dispersed the nucleus into undetectable fragments, or complete depletion of volatile reserves during the intense perihelion heating. Morphology reveals whether the nucleus remains intact or has broken apart. A single compact coma with smooth brightness distribution, centered on a point source, indicates that the object survived perihelion as a coherent body. Multiple condensations within an extended diffuse cloud suggest fragmentation, with separated pieces, each generating their own small coma as exposed ice subliments. Elongated structures or fan-shaped distributions indicate active splitting in progress, material streaming away from a disintegrating nucleus. High-resolution imaging, capable of resolving scales of thousands of kilometers, will distinguish these morphological states definitively within the first week of observations. Spectroscopy provides compositional diagnostics unavailable from brightness or imaging alone. Comparing post-perihelion emission, line intensities against the JWST baseline spectra from September reveals whether the carbon dioxide to water ratio has changed, whether new species have emerged from subsurface layers exposed by erosion, and whether metal emission from nickel or iron continues at previously observed levels. The appearance of new emission lines absent from pre-perihelion spectra would indicate thermal processing exposed chemically distinct materials. The disappearance of previously detected lines suggests depletion of specific volatile reservoirs or changes in excitation conditions within the coma. Non-gravitational acceleration measurements test whether perihelion passage altered the object's trajectory beyond what pure gravitational forces predict. Careful astrometry, tracking the position against background stars over multiple nights, allows orbit refinement to detect accelerations as small as millimeters per second squared. Natural outgassing produces predictable non-gravitational forces proportional to solar heating and directed roughly opposite the Sun. Artificial course corrections would show different timing, magnitude, or directional properties inconsistent with passive thermal response. Detecting such anomalies requires weeks of high-precision measurements, but provides powerful discrimination between natural and engineered scenarios. Color measurements through multiple filters quantify how sunlight scattering depends on wavelength, revealing dust grain properties and coma composition. The controversial blue appearance from the leaked Mars image remains unexplained, making color measurements from multiple viewing geometries particularly valuable. If post-perihelion observations show colors consistent with neutral or reddish dust scattering, that supports the interpretation that the blue smudge was a processing artifact. If blue colors persist or strengthen, that demands physical explanation through either unusual grain populations or reflective surface properties. Light curve monitoring tracks brightness variations over hours to days, revealing rotation periods and testing whether activity modulates with spin state. Natural tumbling produces periodic variations as different surface regions rotate into and out of sunlight. Artificial attitude control might produce different temporal signatures, including unexpected stability or deliberate reorientation maneuvers. The pattern of brightness changes encodes information about shape, rotation, and activity distribution that becomes readable through patient photometric monitoring. These observables transform reappearance from simple redetection into a comprehensive characterization campaign that will either close the book on 3I/Atlas as an unusual but natural comet, or open entirely new chapters in our understanding of what travels between the stars. The astronomical community rarely mobilizes with unified purpose, but 3I/Atlas has triggered coordination across observatories, space agencies, and research institutions on a scale typically reserved for major transient events, like supernova or gravitational wave source counterparts. This coordinated global campaign, planned months in advance and refined as the perihelion window approached, represents humanity's most comprehensive attempt to characterize an interstellar visitor during a critical phase of its solar system passage. The reappearance observations will leverage instruments spanning the electromagnetic spectrum from radio to X-ray wavelengths, distributed across continents to ensure continuous coverage as Earth rotates. The International Astronomical Union serves as the central coordinating body, operating through its Minor Planet Center and various working groups dedicated to small body studies. As soon as any observatory reports confirmed redetection of 3I/Atlas, the information flows through established communication channels to alert facilities worldwide. Standardized observation protocols ensure that different telescopes collect comparable data using consistent filter sets, exposure times, and calibration procedures. This coordination transforms isolated measurements into a coherent dataset that captures the object's properties across multiple dimensions simultaneously. Ground-based optical telescopes form the backbone of the observational campaign. Large facilities in Chile, including the Very Large Telescope and the Gemini South Observatory, provide high-resolution spectroscopy and imaging from Southern Hemisphere locations, where 3I/Atlas first becomes visible. Australian observatories contribute southern sky coverage with complementary instrumentation, while South African facilities add longitudinal diversity that extends the continuous observation window. As December progresses and viewing geometry improves for Northern Hemisphere sites, facilities in Hawaii, the Canary Islands, and the continental United States join the campaign, eventually achieving near 24-hour coverage through coordinated handoffs between continents. Radio telescopes offer capabilities unavailable to optical instruments, potentially detecting molecular emission lines in millimeter and centimeter wavelength ranges that probe different physical conditions within the coma. The Atacama Large Millimeter Array in Chile can map carbon monoxide, hydrogen cyanide, and other molecules with spatial resolution, revealing how gas production varies across the nuclear surface. Radio observations are immune to daylight and weather conditions that plague optical astronomy, allowing continuous monitoring even when visible light telescopes remain idle. The possibility of detecting artificial radio emissions, while considered extremely remote, motivates inclusion of facilities like the Very Large Array in New Mexico, which can conduct sensitive searches for narrowband signals, while simultaneously characterizing natural molecular emission. Space-based assets provide observations free from atmospheric distortion and absorption. The James Webb Space Telescope has allocated follow-up time for 3I/Atlas spectroscopy if the object remains bright enough after perihelion for JWST's sensitivity requirements. These observations would provide direct comparison against the pre-perihelion spectra that established carbon dioxide dominance, revealing any compositional changes driven by thermal processing. The Hubble Space Telescope similarly plans imaging observations to document morphology and track potential fragmentation if the nucleus shows signs of structural failure. Amateur astronomers contribute valuable monitoring that professional facilities cannot match due to telescope scheduling constraints and competing priorities. Dedicated individuals with backyard observatories can track brightness variations nightly, building light curves that reveal rotation periods and activity fluctuations invisible to snapshot observations from large telescopes. The amateur community's flexibility and enthusiasm augment professional campaigns, sometimes capturing transient events like sudden outbursts that occur between scheduled professional observation runs. The coordination extends beyond mere observation to data sharing and rapid analysis. Results flow into online databases accessible to researchers worldwide, allowing near real-time comparison of measurements from different instruments and techniques. Preliminary findings appear in astronomers' telegrams and electronic circulars within hours or days of acquisition, far faster than traditional peer-reviewed publication timelines. This rapid dissemination accelerates scientific progress by enabling researchers to adjust observation strategies based on emerging results, targeting follow-up observations at unexpected features or anomalies as they appear. The global campaign transforms 3I/Atlas from an object of curiosity into a target of intensive scientific scrutiny. The coordination mechanisms, refined through decades of international collaboration on transient phenomena, ensure that humanity's observational capabilities focus on this single visitor with unprecedented comprehensiveness. Whatever 3I/Atlas has become during its passage through the zone, NASA cannot monitor. The world will be watching when it emerges. The James Webb Space Telescope represents humanity's most powerful tool for characterizing the composition of distant objects through infrared spectroscopy, making it uniquely qualified to document any changes 3I/Atlas underwent during perihelion. JWST's near-infrared spectrograph captured baseline observations in late September 2025, revealing carbon dioxide as the dominant volatile with an 8:1 ratio relative to water vapor. Those measurements established the compositional fingerprint against which all future observations would be compared. The December follow-up observations, scheduled for mid-month, when 3I/Atlas reaches optimal viewing geometry, will test whether peak solar heating fundamentally altered the chemical makeup of material escaping from the nucleus. Spectroscopy works by splitting light into component wavelengths and measuring intensity at each specific color, revealing which molecules are present through their characteristic absorption or emission patterns. Carbon dioxide produces strong absorption bands in the near-infrared around 2.7 and 4.3 micrometers, wavelengths where JWST achieves exceptional sensitivity. Water vapor generates its own distinctive pattern of lines at different wavelengths. By comparing the strengths of these features, astronomers derive precise abundance ratios that constrain formation conditions and thermal history. The pre-perihelion carbon dioxide dominance was unusual, but explicable if 3I/Atlas formed beyond the carbon dioxide ice line in its birth stellar system. Water ice sublimes at warmer temperatures than carbon dioxide ice, creating regions in protoplanetary disks where carbon dioxide remains frozen while water has already evaporated or been incorporated into planets. Objects forming in these outer zones naturally acquire carbon dioxide-rich compositions. The question becomes whether perihelion heating exposed deeper layers with different compositions, or whether the 8:1 ratio persists throughout the nucleus. If December spectroscopy shows the carbon dioxide to water ratio has shifted significantly, perhaps dropping to 4:1, or even approaching unity, that indicates erosion-exposed subsurface materials with higher water content. Such stratification would suggest the object formed through multiple accretion episodes in environments with varying temperature and composition, or that surface processing by cosmic rays and ultraviolet radiation over millions of years preferentially removed water from outer layers while leaving deeper ice unaffected. Either interpretation supports natural formation scenarios while revealing complexity in the object's history. Alternatively, if the ratio remains constant at 8:1 despite intense perihelion heating, that suggests compositional homogeneity throughout the nucleus. For a natural comet, this implies formation in highly uniform conditions, where carbon dioxide dominated throughout the accretion process. For those entertaining artificial hypotheses, constant composition might indicate an engineered material chosen for specific properties rather than stochastic accumulation of available ices. New emission features appearing in post-perihelion spectra would prove particularly significant. Detection of ammonia, methane, or complex organic molecules absent from September observations would demonstrate that peak heating liberated volatiles with higher sublimation temperatures, exposing chemically distinct reservoirs. The appearance of unexpected spectral signatures inconsistent with known cometary molecules would demand exotic explanations and trigger intensive follow-up across multiple wavelengths. JWST observations require careful scheduling around the telescope's other commitments and operational constraints. The spacecraft must avoid pointing too close to the Sun, limiting when 3I/ Atlas becomes observable. If the object fades below JWST's sensitivity thresholds due to declining activity or structural dispersal, the follow-up observations might fail to detect sufficient signal for meaningful spectroscopy. Success depends on 3I/Atlas, remaining active and bright through December. December 19th, 2025 represents a convergence of favorable circumstances that astronomers have been anticipating since 3I/Atlas first appeared in July. On this date, the geometric configuration of Earth, Sun, and the interstellar visitor reaches optimal alignment for comprehensive observations from ground-based facilities and space telescopes simultaneously. The object will sit at approximately 1.8 astronomical units from Earth, with angular separation from the Sun exceeding 50 degrees, placing it comfortably outside the exclusion zone in dark sky, accessible to instruments across both hemispheres. This geometry will not repeat, making the 19th a singular opportunity to capture the visitor's properties with maximum clarity before it continues outbound and fades from detectability. Distance matters profoundly in astronomy because light-gathering power and spatial resolution both degrade with increasing separation. At one point, 8 astronomical units, roughly 270 million kilometers, 3I/Atlas remains close enough for moderate-sized telescopes to achieve useful signal-to-noise ratios in reasonable exposure times. Spectroscopy becomes practical for facilities that might struggle to characterize the object at greater distances where photons arrive more sparsely. High-resolution imaging can resolve structures measuring thousands of kilometers across, distinguishing whether the nucleus remains intact or has fragmented into multiple pieces during perihelion passage. The viewing angle on December 19th places 3 I/Atlas in the morning sky before dawn, rising several hours ahead of sunrise and reaching reasonable elevation above the horizon by astronomical twilight. This timing allows extended observation sessions without interference from daylight, critical for accumulating the long integrations required for faint spectroscopic features or detailed morphological mapping. Both northern and southern hemisphere observatories can participate effectively, with the object positioned at moderate declination, accessible from most latitudes. The phase angle, the angle between Sun, object, and Earth, reaches a configuration that enhances certain dust scattering properties while minimizing others. Forward scattering from small dust grains intensifies when viewing geometry, places the observer near the Sun-object line, creating brightness enhancements that reveal dust populations invisible at other angles. The December 19th geometry avoids extreme forward or backward scattering, instead sampling an intermediate phase where multiple grain-size populations contribute to scattered light in ways that constrain dust properties through polarimetry and multi-wavelength photometry. This date also provides temporal separation from perihelion sufficient for transient phenomena to have evolved into stable configurations. Any outbursts triggered by peak heating will have either subsided or developed into sustained activity by 7 weeks post-perihelion. Fragmentation events will have progressed far enough that separated pieces become individually resolvable rather than blending into confused morphology. Non-gravitational accelerations from asymmetric outgassing will have accumulated enough orbital deviation for precise astrometry to detect trajectory changes. The astronomical community has circled December 19th on calendars as a checkpoint, a moment when the accumulated observations since reappearance in late November can be synthesized into comprehensive assessment of what 3 I/Atlas has become. Pre-perihelion properties documented through October will be compared against post-perihelion measurements to quantify exactly what changed during the weeks behind the Sun. The comparison will either confirm that the object behaved as natural comets should, or reveal discrepancies that demand we reconsider what passed through the zone NASA could not monitor. Telescope time has been allocated, observation plans have been submitted and approved, and instrument configurations have been optimized for the expected brightness and spectroscopic requirements. Weather permitting and assuming the object cooperates by remaining bright enough for detection, December 19th will deliver the most detailed snapshot of an interstellar visitor ever captured during optimal observing conditions. What that snapshot reveals will shape our understanding of 3 I/Atlas and inform how we interpret future interstellar objects that follow similar trajectories through our cosmic neighborhood. The perihelion blackout creates a fundamental imbalance in knowledge that extends beyond mere scientific frustration into questions about cosmic awareness and strategic vulnerability. For 6 to 8 weeks, 3 I/Atlas operates in an environment where human observers possess zero real-time information about its state, behavior, or evolution. If the object is natural, this asymmetry carries no deeper meaning beyond the limitations of our observational geometry. But if the visitor possesses any form of autonomous capability, whether biological or artificial, the blackout period represents a window where actions can occur without detection, until their consequences become observable weeks later. Information asymmetry in strategic contexts describes situations where one party knows more than another, creating advantages that can be exploited for negotiation, competition, or conflict. In terrestrial affairs, intelligence agencies expend vast resources to achieve informational advantages over adversaries, knowing that superior knowledge enables better decision-making and tactical positioning. The perihelion blackout inverts this relationship for humanity, placing us in a position of near total ignorance, while the object itself, if it possesses senses or awareness, experiences uninterrupted knowledge of its own state and surroundings. The timing of the blackout coinciding with perihelion amplifies the asymmetry's significance. This is not a random observational gap, but rather the loss of visibility during the most operationally critical phase of the solar system traverse. Maximum available energy, peak thermal stress, optimal conditions for trajectory modifications all occur precisely when Earth-based civilization cannot observe. A natural object follows physics regardless of whether observers watch, making the timing merely unfortunate. An engineered system could theoretically recognize that perihelion passage through solar conjunction provides maximum operational flexibility with minimum detection risk. The concept does not require deliberate mission planning or advanced knowledge of Earth's position. Simple autonomous logic responding to local conditions would suffice. A probe programmed to activate systems when solar flux exceeds thresholds, adjust course when delta V efficiency peaks, or conduct observations when stellar proximity allows maximum data collection would naturally concentrate activities near perihelion. That these activities coincidentally occur during Earth's observational blackout emerges from orbital geometry rather than coordination. The asymmetry is built into the configuration of the solar system itself. This creates an epistemological trap where we cannot distinguish between scenarios based on perihelion observations because we have no perihelion observations. We can model what should happen under various assumptions. We can predict outcomes for natural versus artificial scenarios, but we cannot test those predictions against reality during the critical window. By the time 3I/Atlas reappears in observable sky, any actions taken during the blackout become historical facts, whose causes we must infer from limited effects rather than observed processes. The asymmetry persists even after reappearance. We will see what 3I/Atlas has become, but not how it became that way. If trajectory has changed, we detect the new orbit, but not the maneuver that created it. If brightness has evolved unexpectedly, we measure the result, but not the mechanism. If composition shows anomalies, we characterize the chemistry, but not the process that altered it. The blackout permanently removes a crucial chapter from the observational record, leaving gaps that speculation fills in the absence of data. For a natural comet, these gaps matter only to scientific completeness. For an artificial probe, they represent windows of opportunity where actions occur beyond human awareness, a strategic advantage built into celestial mechanics itself. We cannot know which case applies until reappearance provides the first clues about what happened in the zone NASA could not monitor. The history of comet observations includes numerous examples of objects that approach the Sun expecting to survive perihelion passage, but instead fragmented, vaporized, or simply vanished from detectability. These precedents establish that structural failure during closest solar approach represents a common outcome rather than an exceptional event, particularly for comets making unusually close passes, or experiencing perihelion for the first time after long dormancy in cold storage. The fate of 3 I/Atlas remains uncertain precisely because natural objects frequently fail to survive the thermal and mechanical stresses imposed by intense solar heating. Comet Ison in 2013 generated enormous public anticipation as it approached an extremely close perihelion at just 0.012 astronomical units from the solar surface, barely 1.8 million kilometers above the photosphere. Predictions suggested it might become spectacularly bright, potentially visible during daytime if it survived intact. Instead, observers watched through SOHO coronagraph images as the comet entered perihelion and simply failed to emerge. The nucleus apparently disintegrated completely under extreme heating that vaporized its icy components and dispersed dust into an expanding cloud that quickly faded below detectability. What should have been the astronomical event of the year became a lesson in cometary fragility. Comet Lovejoy in 2011 followed an even closer trajectory, passing just 0.008 astronomical units from the solar surface as a member of the Kreutz Sungrazer family. Unlike Ison, Lovejoy surprised observers by surviving its perihelion passage, despite predictions that it should have been destroyed. The comet emerged from behind the Sun diminished but intact, eventually becoming a spectacular naked-eye object visible from southern hemisphere locations. The survival demonstrated that structural strength varies enormously among comets, with some nuclei cohesive enough to withstand thermal stress that destroys others. The Kreutz Sungrazer family provides the most extreme examples, consisting of hundreds of small comets that plunge to within a few solar radii before complete vaporization. These objects, discovered primarily through SOHO coronagraph observations, rarely survive perihelion. Most simply fade from view as solar heating overwhelms their limited mass, converting ice directly to gas and scattering dust into undetectable dispersal. The family likely originated from fragmentation of a single large progenitor, comet centuries or millennia ago, with pieces following similar orbits on collision courses with the Sun. 3 I/Atlas faces far less extreme conditions at 1.36 astronomical units, roughly 140 times more distant from the solar surface than the Kreutz Sungrazers. This distance places it well outside the realm where complete vaporization becomes likely. However, the object's interstellar origin introduces uncertainties that solar system comets do not face. Material that formed in another stellar system and spent millions of years in interstellar space might possess different structural properties than local comets. Cosmic ray bombardment, micrometeoroid impacts, and thermal cycling during the long journey could have weakened internal cohesion, creating fracture planes that fail under stress that freshly formed solar system comets would survive. The historical precedents establish that even at modest perihelion distances, comets can fragment, fade, or vanish entirely. 3 I/Atlas might emerge intact and active, continuing its journey through the outer solar system as a coherent object. Or it might join the list of visitors that approach the Sun with structure intact, but left as dispersing debris clouds, their structural integrity insufficient to survive the trial by fire that perihelion imposes on all who venture near our star. Orbital mechanics dictate that small velocity changes applied near perihelion produce disproportionately large effects on final trajectory, through what engineers call the Oberth effect, named after the rocket pioneer who first quantified how gravity assists amplify propulsive efficiency. A spacecraft or object executing a maneuver deep in a gravitational well achieves far greater changes to orbital energy than the same maneuver performed in weakly curved space far from any massive body. This mathematical reality means that perihelion represents the optimal location for any course corrections 3I/Atlas might execute, whether through natural outgassing forces or hypothetical artificial propulsion systems. The physics underlying the Oberth effect involves kinetic energy scaling with the square of velocity. Near perihelion, objects move fastest as they fall toward the Sun and convert gravitational potential energy into motion. Adding velocity at this high-speed point increases kinetic energy more efficiently than adding the same velocity increment when moving slowly. The difference can be dramatic, with delta V applied at perihelion, producing 2 or 3 times the orbital energy change compared to identical thrust applied at aphelion far from the Sun. For 3I/Atlas, the trajectory modifications achievable through modest perihelion maneuvers could redirect the object toward entirely different destinations in the outer solar system. The current orbit carries it past Jupiter in March 2026 at approximately 0.36 astronomical units distance. A velocity change of just a few meters per second applied during perihelion passage could alter the Jupiter encounter distance significantly, transforming a distant flyby into a close approach or steering the object away from Jupiter entirely toward different targets. Larger maneuvers measuring tens of meters per second could fundamentally reshape the trajectory, potentially directing 3I/Atlas toward Saturn, Uranus, or even back toward the inner planets for additional passes. Natural outgassing provides plausible mechanisms for velocity changes without invoking artificial propulsion. Asymmetric sublimation from the sunward hemisphere creates thrust as gas molecules carry momentum away from the nucleus. For a nucleus several kilometers across, releasing thousands of kilograms per second of gas, accumulated thrust over days near perihelion could produce velocity changes of several meters per second. These natural forces already account for non-gravitational accelerations in many solar system comets, explaining why orbits deviate slightly from pure Keplerian motion. Distinguishing natural outgassing from artificial propulsion requires careful orbit determination through precise astrometry after perihelion. Natural forces should correlate with solar heating, reaching maximum near perihelion and declining predictably with distance. The direction should point roughly opposite the Sun, consistent with gas escaping from illuminated surfaces. Artificial propulsion might show different timing, activating suddenly rather than smoothly varying with distance, or different directionality inconsistent with thermal gradients. The perihelion blackout means we cannot observe any maneuvers as they occur. By December, any course corrections will be historical facts encoded in the object's new trajectory. Comparing the actual orbit against predictions will reveal whether significant velocity changes occurred. Small deviations might remain ambiguous between natural outgassing and controlled thrust. Large trajectory alterations would demand explanations natural forces cannot easily provide. When 3I/Atlas reappears in late November or early December 2025, astronomers will immediately compare post-perihelion properties against the October baseline. This comparison transforms abstract speculation into testable hypotheses. 3 broad outcome categories encompass the realistic possibilities, each carrying distinct implications for understanding what passed through the zone NASA could not monitor. The first possibility involves the object returning essentially unchanged or evolving as predicted for natural comets. Brightness would follow expected decline curves as outgassing decreases with growing solar distance. Spectroscopy would show the same carbon dioxide dominance JWST observed in September, possibly with slightly altered ratios if erosion exposed compositional variations. Morphology would display a single intact nucleus surrounded by coma, consistent with rotation and thermal gradients. The orbit would show only small deviations, attributable to natural non-gravitational accelerations. This outcome would confirm 3I/Atlas as an exotic but fundamentally natural interstellar comet. The second possibility involves fragmentation or structural failure that disperse the nucleus. Multiple condensations would appear where observations showed a single object, each fragment generating its own small coma. Brightness might temporarily spike during breakup as fresh surfaces release volatiles, then fade rapidly as fragments deplete reserves and disperse along diverging trajectories. This would demonstrate insufficient structural strength to survive perihelion thermal stress. The third possibility encompasses unexpected changes, defying straightforward natural explanations. The object might emerge brighter than predicted without fragmentation, suggesting delayed outbursts or compositional anomalies. Trajectory could show non-gravitational accelerations, too large or wrongly directed for natural outgassing. Spectroscopy might reveal new features inconsistent with cometary chemistry. Morphology could display asymmetries incompatible with random nucleus shapes and thermal gradients. These outcomes would demonstrate that 3I/Atlas behaves differently than natural comets in ways requiring exotic physics. The re-emergence observations will provide answers, but not necessarily closure. The data will constrain scenarios and eliminate some possibilities, while leaving others viable, advancing understanding, even if definitive conclusions remain elusive. What re-emergence tells us depends entirely on what 3I/Atlas became. During the weeks, we could not see it changing. The story does not end with perihelion passage or December re-emergence. The trajectory carries the visitor toward Jupiter, with closest approach scheduled for March 16th, 2026, at 0.36 astronomical units from the gas giant. This distance places it outside Jupiter's major satellites, but close enough for gravitational interactions to alter trajectory and provide observation opportunities from NASA's Juno spacecraft orbiting the planet. The gravitational encounter will deflect 3I/Atlas's trajectory through a slingshot effect, adding or subtracting orbital energy depending on flyby geometry. Tracking the post-Jupiter orbit will reveal how much the trajectory changed, providing another data point for constraining mass through gravitational dynamics. Any additional non-gravitational accelerations will appear as deviations from purely gravitational predictions. Beyond Jupiter, 3I/Atlas faces a long journey outward, gradually fading as distance increases and solar heating declines. The object will eventually exit the planetary region entirely, returning to interstellar space on a trajectory forever altered by its passage through our solar system. The perihelion blackout remains a permanent gap in the observational record, a chapter we can never fully reconstruct from direct observation. What 3I/Atlas became during those invisible weeks will be inferred from before and after comparisons. The story continues beyond the zone NASA could not monitor, but that zone forever shapes everything that follows.